Today I'll be talking about conservation of momentum in collisions in one or two dimensions. Total linear momentum is conserved when two or more objects collide, provided they constitute an isolated system. In other words, no external forces. And we can think of these type of interactions or collisions in three categories. The first is being totally elastic. In this case, the total kinetic energy of the system before and after the collision is equal as well as the momentum. Here's a little illustration. If you drop a ball, hits the ground, bounces back up the same height, the kinetic energy before must be equal to kinetic energy after. And momentum is obviously conserved as well. An inelastic collision is one in which the total kinetic energy of the system after collision is not equal to the total kinetic energy before the collision. So this is like what happens basically almost like in real life. This is really mostly an idealized situation. But you drop a basketball, collides with the ground, and it obviously doesn't come up to the same height. So kinetic energy was not the same before and after. And completely inelastic is when you drop the basketball and it sticks together. The two objects actually stick together. And we'll be looking at two cases, two idealized cases. The elastic collisions and the completely inelastic collisions. We'll do the completely inelastic collisions first. So, completely inelastic collisions. Collision where momentum is conserved, but kinetic energy is not, and the objects stick together. So here you got two objects. They're coming in together, M1 and M2, and they hit into each other, stick together, and move off with some final velocity. So here you have the initial momentum of 1, the initial momentum of 2, and the two of them stick together and move off with some final velocity. Let's look at an example of that. Now this example is going to combine a couple different ideas, one from conservation of energy and conservation of momentum. So it's a good review problem. You have a ballistic pendulum, and basically what you do is you shoot a bullet into this pendulum and it swings up, and you're able to therefore go back and calculate how fast the bullet was initially going. Yeah, the mass of the wooden block is 2.5 kilograms. The mass of the bullet is pretty small, 0.0100 kilograms. And once it hits into the block and the bullet swing up a height of 0.650 meters above the initial position. And what we're trying to do is figure out this initial velocity of the bullet. So we're going to break this into two parts. One, the bullet hitting the block, and two, or B, the block and the bullet swinging upwards. Okay? The first part is conservation of momentum. And we know the final momentum must be equal to the initial momentum because there's no external forces. So we have our conservation of momentum equation, where we have the final momentum of the two objects must be equal to the initial momentum of the two objects. But since the initial momentum of the wooden block was 0, this term will drop out. And the final momentums, the two masses stick together to form some final velocity. Why do we add the two masses together? Because they're both taking off at the same final velocity, so they became one object. So this is a totally inelastic collision. And we can therefore solve for this initial velocity. But the problem is we don't know what this final velocity is yet. Okay? So we're going to have to do the second half of the problem now, and then use that to find the final velocity, and plug that in to get the initial velocity. So here we go. The second part of the equation is actually using conservation of energy. We know the final potential plus the final kinetic has to equal the initial potential plus the initial kinetic. And we know the the final kinetic has to be 0 because the final speed at the maximum height is 0. And we can assume the initial potential energy is 0 because the height is 0. We'll set that equal to 0. So we really come down as mgh is equal to 1/2 mv squared. And we know the masses are both masses because they're stuck together, mass 1 and mass 2. But it really doesn't matter because they're on both sides of the equation anyhow. And we can solve for our final velocity, which is really the initial velocity taking off in this case, right? It's the final velocity of part A, but it's the initial velocity of part B. And we can take this term and plug it back into our original equation. There's our final velocity, and we'll plug it into our initial equation and put the numbers in, and there we can calculate what the initial speed of the bullet was, 896 meters per second. So this was a good review problem because it made us look at both conservation of energy and conservation of momentum. And this is an example of a totally inelastic collision. All right. Elastic collisions. This is a collision with both momentum and kinetic energy are conserved. This is really another idealized case. You have the two objects coming in, they collide, and they bounce off without any loss of kinetic energy. So not only is momentum conserved, the two objects come in together, here's the initials, and they bounce off at some finals, but also kinetic energy is conserved. So if you think of this, now we have two equations, therefore we could have two unknowns. Okay? And we'll talk more about this type of problem in class. Now, I just want you to understand that the principles of conservation of momentum or linear momentum are still can be applied when the collisions occur in two dimensions. And here's the reason why. Let's look at this one object here. This is the final velocity of object 1 after colliding. So you get one object coming in and collides with another object. They both move off in different directions. But let's look at this one object here. You can find out how much its final velocity in the y is and what the final velocity in the x is. And you could do that with every term. You could do it with this one, and this one. And really what you could do then is apply the conservation of momentum to both the x direction and the y direction and find out the answers. It's a little bit more complicated, but it's the same principle. Okay?